There's a faint whisper echoing across the universe, a ghostly afterglow from the very beginning of time itself. It's called the cosmic microwave background, and it's the oldest light we can see, a relic from the moment our cosmos burst into existence nearly 14 billion years ago. Picture this: every time you tune an old television to static, a small fraction of that snow is actually the distant echo of the Big Bang, reaching out to us from the edge of space and time. But this isn't just ancient radiation, it's a treasure map, packed with clues about how the universe was born, how it grew, and what secrets still lie hidden in the fabric of reality. Scientists call it the CMB for short, and it's one of the most profound discoveries in human history. Imagine holding a photograph of the universe as a newborn, just 380,000 years after its fiery birth. That's what the cosmic microwave background gives us, a snapshot of the cosmos in its infancy, frozen in light. Yet, the deeper we look, the more mysteries we uncover. Strange anomalies, unexplained patterns, and cosmic contradictions lurk within this glow, challenging everything we thought we knew about space, time, and the very laws of physics. Some of these puzzles hint at realities beyond our own parallel universes, hidden dimensions, or even flaws in the fabric of spacetime itself. That's where our journey begins. Today, we're diving into the 25 most mind-bending mysteries of the cosmic microwave background, enigmas that have left even the brightest astrophysicists scratching their heads. From bizarre cold spots that defy explanation to eerie alignments that seem to point toward something beyond our universe, each of these cosmic riddles pulls us deeper into the unknown. What if these anomalies aren't just glitches, but messages, whispers from a reality far stranger than we ever imagined? Buckle up, because we're about to explore the edges of our understanding, where the answers we find might just rewrite the story of everything. One of the most baffling features of the cosmic microwave background is how eerily uniform it appears. No matter where we point our telescopes, the temperature of this ancient light is almost exactly the same, down to a few millionths of a degree. At first glance, this might not seem strange, but when you consider the sheer size of the universe, it becomes a paradox. Here's why: the cosmos simply hasn't had enough time for heat to spread evenly. Think of two cups of coffee on opposite sides of a room. If left untouched, they'd never reach the same temperature naturally unless something stirred them together. Now imagine those cups are billions of light years apart, separated in the early universe before light or heat could possibly travel between them. Yet, the CMB shows they somehow did reach the same temperature. Scientists call this the horizon problem, and it's one of the biggest unresolved puzzles in cosmology. To explain it, physicists proposed something called cosmic inflation, a theory suggesting the universe expanded faster than light itself in the first fractions of a second after the Big Bang. This would have smoothed everything out like stretching a wrinkled sheet until it's flat. But while inflation solves the uniformity problem, it's not without issues. For one, we've never directly observed the particle or force that could have driven such rapid expansion. Worse, some versions of inflation predict too much uniformity, while the real CMB has subtle, unexplained variations that don't quite fit the model. Alternative ideas have emerged, like theories suggesting the early universe was smaller than we thought, allowing heat to spread more easily. Others propose our universe is just one bubble in a vast multiverse, where countless other universes exist with different physical laws. But these ideas are even harder to test, leaving the horizon problem wide open. The unsettling truth that perfect uniformity we see might be hinting at something fundamental we're still missing, a hidden chapter in the story of how everything began. But the mysteries don't end with the horizon problem. Lurking in the cosmic microwave background is something even stranger, a chilling anomaly known simply as the cold spot. Picture a vast, unexplained patch of space where the temperature dips significantly lower than its surroundings. as if a cosmic freezer door was left slightly ajar in the early universe. This isn't just a minor fluctuation, it's a glaring outlier stretching over 1 billion light-years, and it defies everything we expect from the standard model of cosmology. At first, scientists thought it might be a statistical fluke, a random blip in the data. But as observations improved, the cold spot stubbornly remained, its existence confirmed by multiple telescopes. The odds of such a feature appearing by pure chance, less than 2%. So what could possibly cause a region of the universe to be so unnaturally cold? One leading theory points to something called a supervoid, an enormous, nearly empty bubble of space where galaxies and matter are unusually sparse. In such a void, light traveling through it would lose energy, creating a cooler patch in the CMB. But here's the catch: even the largest supervoids we found don't fully explain the cold spot's extreme temperature drop. It's like trying to explain a blizzard with a light breeze. The numbers just don't add up. This has led to far wilder possibilities. Some researchers suggest the cold spot could be evidence of a collision with another universe, a bruise left by a cosmic crash between our reality and a parallel one in the multiverse. Others propose it's a rare imprint of exotic physics, like primordial black holes or defects in spacetime itself. But these ideas, while thrilling, remain untested, leaving the cold spot one of the most tantalizing unsolved puzzles in modern astrophysics. What makes this anomaly so unsettling is that it challenges not just one, but multiple pillars of our understanding. If it's a supervoid, why is it so much colder than it should be? If it's something more exotic, why haven't we found any other traces? The cold spot stands as a cosmic riddle, daring us to rethink the very foundations of our universe, or to consider the possibility that some mysteries are so deep they may forever lie just beyond our grasp. If the cold spot left you unsettled, wait until you hear about the so-called axis of evil, a bizarre pattern in the cosmic microwave background that has physicists questioning whether the universe might have a preferred direction. Normally, the CMB's temperature fluctuations should be random, scattered like confetti across the sky. But when researchers mapped these variations, they found something shocking. Certain hot and cold spots appear strangely aligned along a specific axis, as if the universe itself had a hidden spine. This alignment, whimsically nicknamed the axis of evil, contradicts one of cosmology's foundational principles, the idea that the universe is isotropic, meaning it should look the same in all directions. Instead, this eerie pattern suggests a cosmic asymmetry, as if some ancient structure or force imprinted itself on the fabric of reality before the Big Bang. At first, scientists dismissed it as a statistical illusion, a trick of the data. But the more we've studied it, the harder it becomes to ignore. The odds that such an alignment happened by chance: less than 1 in 1,000. So what could possibly cause such a lopsided imprint on the universe? One radical theory proposes that the axis of evil is a fossil from a previous cosmic cycle, a scar left behind by a universe that existed before ours. Some versions of string theory even suggest that our universe might have collided with another, warping space-time in a way that created this peculiar axis. Others speculate about undiscovered forces or fields that once dominated the early cosmos, stretching reality along an invisible line we're only now detecting. But here's the catch: if the axis of evil is real, it doesn't just challenge our models, it upends them entirely. The standard cosmology playbook relies on a universe without preferred directions, where the laws of physics hold equally everywhere. If the cosmos has a tilt, though, we'd need to rewrite the rules. The controversy is so heated that some researchers argue we're misinterpreting the data, while others believe we're glimpsing evidence of a reality far stranger than we've dared to imagine. What makes this mystery especially thorny is that it blurs the line between science and philosophy. Are we seeing noise or a message from beyond the dawn of time? For now, the axis of evil remains one of the most divisive puzzles in cosmology, a cosmic riddle that either exposes a flaw in our observations or a crack in the very foundation of physics itself. Just when you think the cosmic microwave background can't get any more perplexing, we stumble upon another head-scratcher, the case of the missing large-scale fluctuations. According to our best models of the universe's birth, the CMB should display a certain pattern of temperature variations across vast distances, like ripples frozen in time from the Big Bang's explosive energy. But when scientists measured these ripples, something was off. The largest fluctuations, the ones spanning billions of light-years, were strangely muted. It's as if the universe hit a cosmic volume knob and turned down the bass, leaving astrophysicists scrambling to explain why. This so-called missing power problem isn't just a minor hiccup, it strikes at the heart of how we understand the universe's infancy. The standard cosmological model, backed by decades of meticulous calculations, predicts that gravitational waves and quantum fluctuations in the early cosmos should have imprinted larger temperature differences on the CMB than what we actually observe. Imagine tossing a handful of pebbles into a pond and expecting big waves, only to see tiny, barely noticeable ripples. That's the level of discrepancy we're dealing with here. One possible explanation involves tweaking our understanding of inflation, the universe's rapid expansion in its first moments. Maybe inflation didn't happen quite as smoothly as we thought, or perhaps it shut off earlier than expected, leaving less time for those large-scale fluctuations to amplify. Some theorists even speculate that the universe's geometry might be more complex than we realize, curved in ways that suppress certain wavelengths of these primordial ripples. But the plot thickens when we consider alternatives that venture beyond conventional physics. Could there have been an unknown force or particle at play in the early universe, one that dampened these fluctuations before they could grow? Or does the missing power hint at something even more profound, like our universe being part of a multiverse where the rules of physics vary from one cosmic bubble to another? The stakes here are enormous. If our models are wrong about these initial conditions, it could mean rethinking everything from the birth of galaxies to the ultimate fate of the cosmos. Yet every time we try to patch one hole in our theories, another mystery opens up. The missing fluctuations stand as a silent challenge, a cosmic whisper urging us to dig deeper, because somewhere in that faint afterglow, the universe might be trying to tell us something we're not yet ready to hear. Among the many peculiarities hidden in the cosmic microwave background, few are as persistent or as perplexing as the strange alignment of its largest temperature patterns. Scientists refer to these patterns as multipoles, with the quadrupole and octupole being the most prominent. In simple terms, the quadrupole describes how the CMB temperature varies across 4 broad sections of the sky, while the octupole covers 8. According to our standard models, these patterns should be randomly oriented, like dice tossed onto a table. Yet when we map them, they appear suspiciously aligned, as if some unseen hand guided their arrangement. This alignment isn't just a minor curiosity, it's a direct challenge to one of cosmology's bedrock assumptions, that the universe is fundamentally uniform with no preferred direction or axis. The odds of these multipoles lining up purely by chance are astronomically low, less than 1 in 1,000. So why does the universe seem to have a hidden preference? One camp argues it's an illusion, a trick of perspective caused by our own motion through space or subtle errors in how we process the data. After all, Earth isn't stationary. We're hurtling through the cosmos at over 1 million miles per hour, which could theoretically skew our observations. But even after accounting for this motion, the alignment stubbornly persists, leaving the mystery intact. Others propose more radical explanations. Could this alignment be a relic of an era before the Big Bang, a fingerprint of some primordial structure that shaped the newborn universe? Some theories suggest these patterns might trace back to quantum fluctuations frozen into spacetime during inflation, stretched to cosmic scales but retaining an unexpected coherence. Even wilder ideas float around, like the possibility that our universe is bumping up against the boundaries of a larger, unseen dimension, warping the fabric of reality in ways we're only beginning to detect. But here's the twist: if the alignment is real, it doesn't just hint at new physics, it demands it. The standard model of cosmology has no room for such coordinated patterns on such vast scales. Either we're missing a critical piece of the puzzle, or we're glimpsing evidence of forces and phenomena that lie entirely outside our current understanding. The debate rages on, with some researchers calling for better data from future telescopes, while others quietly wonder if this is our first clue that the cosmos is far stranger and far more intricate than we ever dreamed. Diving deeper into the cosmic microwave background's enigmas, we encounter something even more subtly bizarre: an unexpected preference for symmetry hidden in its ancient light. Scientists call it the parity problem, and it's as puzzling as flipping a coin thousands of times only to find it consistently lands heads up far more often than tails. In the language of physics, parity refers to whether patterns in the CMB mirror evenly across space, even parity, or twist asymmetrically, odd parity. According to our best models, the universe should produce both types equally, yet when we analyze the data, even parity patterns dominate in a way that defies statistical expectations. This imbalance isn't just a minor quirk, it challenges the assumption that the early universe was fundamentally unbiased, governed by laws that treat all directions and symmetries equally. One school of thought suggests the anomaly might stem from something as mundane as measurement errors. Perhaps our telescopes are inadvertently filtering out odd parity signals or misinterpreting noise. But repeated observations, including data from satellites like Planck, keep confirming the same skew, leaving the instrument theory on shaky ground. That's where the explanations get far more intriguing. Some theorists propose that the universe might have an exotic shape, a twist in cosmic topology akin to a hall of mirrors where space loops back on itself in ways that amplify even parity patterns. Imagine light traveling across such a universe and returning to its starting point after circumnavigating a hidden dimension. The geometry could subtly favor certain symmetries over others. Others speculate about primordial magnetic fields or undiscovered particles that polarized the CMB's light billions of years ago, imprinting this odd preference into the fabric of spacetime itself. Yet the most radical ideas venture into uncharted territory. Could the parity problem be a fossil from a pre-Big Bang era, a relic of conditions we can't yet observe? Or does it hint at a deeper asymmetry in the laws of physics, one that might even explain why our universe is made of matter rather than antimatter? The unsettling truth is that no single theory has yet gained widespread acceptance. The parity anomaly remains a quiet but persistent thorn in cosmology's side, a whisper from the early universe that we're still struggling to translate. What makes this mystery so compelling is its quiet defiance. Unlike dramatic cold spots or eerie axes, the parity problem doesn't announce itself boldly. It lingers in the fine print of the data, a statistical ghost that refuses to vanish. And that's precisely why it's so dangerous to ignore. In science, it's often the subtlest anomalies that lead to the biggest revolutions. If the universe truly has a hidden preference for symmetry, it might be quietly pointing us toward a reality far stranger than we've ever imagined. Among the cosmic microwave background's most hotly debated anomalies is a phenomenon so strange, it sounds like something from science fiction dark flow. Picture this: hundreds of galaxy clusters, each containing thousands of galaxies, all drifting in the same direction at nearly 2 million miles per hour, as if tugged by some invisible hand beyond the edge of the known universe. This isn't the random motion we'd expect from cosmic expansion, but a coordinated migration, one that seems to leave a faint fingerprint in the CMB's temperature patterns. The discovery first made waves in 2008, when astronomers analyzed data from the Wilkinson microwave anisotropy probe and noticed a peculiar dipole signal, a distortion in the CMB's heat map that couldn't be explained by our galaxy's motion alone. Instead, it hinted at something far more unsettling: vast swaths of matter moving en masse toward a single patch of sky near the constellations Centaurus and Vela. The implications were staggering. If real dark flow suggested the presence of colossal, unseen structures, perhaps other universes or regions of space-time, exerting gravitational influence from beyond the observable cosmos. Skeptics were quick to push back. Could this just be an artifact of incomplete data or calibration errors? Some argued that foreground emissions from our own galaxy might be contaminating the CMB signal, creating the illusion of motion where none exists. Others pointed out that newer observations, like those from the Planck satellite, failed to detect the effect at the same magnitude. Yet, intriguingly, Planck's data didn't entirely rule it out either. It merely suggested the flow might be subtler than first thought. The debate hinges on a deeper question: how can anything outside our universe affect what's inside? If dark flow is real, it might mean our cosmic neighborhood is just a small part of something unimaginably larger, a multiverse where other bubble universes float like islands in an infinite sea. Their gravity could subtly pull on ours, like the moon tugging at Earth's tides. But here's where things get even weirder. Alternative theories propose that dark flow isn't caused by external forces at all, but by irregularities in the very fabric of space-time left over from inflation. Imagine the early universe as a rubber sheet stretched unevenly. Some regions might have retained a slight wrinkle, creating a preferred direction for matter to stream toward. If true, this would mean dark flow isn't a window to other universes, but a fossil of our own universe's turbulent birth. Whatever the answer, dark flow forces us to confront the limits of our knowledge. Is it a phantom in the data, or the first glimpse of a cosmos vaster than we ever dared to imagine? For now, the mystery lingers, a silent current in the cosmic dark, pulling us toward questions we're only beginning to ask. If the cosmic microwave background has taught us anything, it's that the universe loves a good puzzle, and one of its most baffling involves the ghostly presence of dark matter. This mysterious substance makes up about 25% of the cosmos, and its gravitational fingerprints are all over the CMB. The patterns in this ancient light reveal how dark matter's gravity sculpted the early universe, pulling matter into the cosmic web that eventually formed galaxies. But here's the catch: while the CMB gives us a crystal-clear picture of dark matter's effects, every attempt to detect the particles themselves has come up empty. It's like hearing the roar of an invisible beast but finding no footprints in the snow. This discrepancy has scientists scrambling. On one hand, the CMB's data, collected by satellites like Planck, paints dark matter as a slow-moving, cold substance that clumps together gravitationally. This fits beautifully with how we see galaxies and clusters forming. But when physicists set up ultra-sensitive experiments deep underground to catch dark matter particles directly, the detectors remain eerily silent. These experiments, like Xenon and Lux, are designed to spot dark matter bumping into ordinary atoms, yet after decades of searching, not a single convincing signal has emerged. The question isn't just frustrating, it's existential. Are we wrong about what dark matter actually is? One possibility is that dark matter isn't made of the heavy, sluggish particles we've been hunting. Alternative theories suggest it could be warmer, lighter, or even interact with ordinary matter through forces we haven't discovered yet. Imagine dark matter as a shadow that only gravity can touch, otherwise it slips through the universe unnoticed. Another radical idea is that dark matter isn't particulate at all, but a fluid-like substance or a defect in spacetime itself. The stakes couldn't be higher. If our models of dark matter are flawed, it doesn't just affect particle physics, it ripples outward, forcing us to rethink how galaxies evolved, how the cosmos structured itself, even how the Big Bang unfolded. Some researchers argue the CMB might be hinting at something even stranger, that dark matter's properties changed over time, behaving one way in the early universe and differently today. Others whisper about the possibility that gravity itself works differently on cosmic scales, eliminating the need for dark matter entirely. What makes this mystery so gripping is its duality. The CMB and direct detection experiments are both incredibly precise, yet they're telling two different stories. Either we're missing a crucial piece of the puzzle, or the universe is playing a trick on us, hiding its secrets in plain sight. Until we solve this riddle, dark matter remains both the scaffolding of the cosmos and its most elusive phantom. The cosmic microwave background isn't just a snapshot of the early universe, it's also a cosmic recipe book, preserving the exact conditions that forged the first atoms. According to the standard model of Big Bang nucleosynthesis, the intense heat of the newborn cosmos cooked up specific amounts of hydrogen, helium, and trace elements like lithium. The math is precise. The CMB's temperature fluctuations let us calculate exactly how much lithium should exist in the universe today, but there's a glaring mismatch. When astronomers measure lithium in ancient stars, the ones that formed from nearly pristine material, they find only a third of what the models predict. This isn't a minor rounding error, it's a full-blown crisis called the lithium problem, and it threatens to unravel our understanding of the universe's first moments. So where did all the lithium go? One camp argues the answer lies in nuclear physics. Maybe our models oversimplify how lithium-7, the isotope in question, formed during nucleosynthesis. Tiny adjustments to reaction rates or unknown nuclear resonances could theoretically deplete the expected abundance, but decades of lab experiments have failed to find gaps large enough to explain the discrepancy. Others propose that lithium gets destroyed inside stars over billions of years, sinking from their atmospheres into hotter interior layers where nuclear reactions break it apart. The catch: even the oldest, most chemically untouched stars show the same lithium shortage, suggesting the problem started before stars existed. That's where things get wild. Some theorists suggest exotic fixes, like hypothetical particles called actions, sneaking out of the early universe and carrying away energy that would have otherwise produced more lithium. Others float the idea of primordial black holes evaporating in the first seconds after the Big Bang, altering the density of matter during nucleosynthesis. The most radical solutions even involve alternative theories of gravity or dark matter interactions skewing the nuclear balance. What makes the lithium problem so stubborn is that it pits two rock-solid pillars of science against each other: the CMB's pristine predictions and the impeccable data from stellar spectroscopy. Both can't be wrong, so either we're missing a fundamental piece of nuclear physics, or the early universe played by rules we haven't discovered yet. Every failed solution only deepens the mystery, leaving us to wonder, is the cosmos hiding a secret ingredient, or have we misread the recipe entirely? The cosmic microwave background holds more than just temperature patterns. It also carries imprints of an epic cosmic transformation known as reionization. Picture the early universe as a foggy void, filled with neutral hydrogen gas so dense it absorbed all light. Then something happened. Within a billion years of the Big Bang, this fog lifted as violent bursts of radiation tore electrons from atoms, transforming the cosmos into the transparent expanse we see today. The CMB's polarization pattern's subtle swirls in its ancient light act as a fossil record of this upheaval. But here's the puzzle: the story they tell doesn't match what our models predict. Instead of a smooth, early transition, the data suggests reionization was messy, drawn out, and surprisingly late. Conventional wisdom pointed to the first galaxies as the culprits, their newborn stars flooding the universe with ultraviolet light. But when astronomers calculate how quickly these early galaxies could have formed, the numbers fall short. the CMB implies reionization didn't wrap up until around 900 million years after the Big Bang, far later than simulations suggest it should have. Even stranger, the polarization patterns hint that the process wasn't uniform. Some regions of space became transparent earlier than others, like patches of ice melting at different rates under a flickering sun. This leaves scientists scrambling for explanations. Could supermassive black holes in the early universe have contributed, their voracious appetites spewing X-rays that helped strip electrons from hydrogen? Or might there have been exotic particles decaying dark matter, perhaps releasing enough energy to kickstart reionization before stars took over? Some theorists propose an even wilder idea, that the first stars weren't just hot but monstrous, with early galaxies hosting behemoths hundreds of times heavier than our Sun. These cosmic titans would have burned furiously and died young, seeding space with enough radiation to explain the patchy timeline. Yet every hypothesis comes with hurdles. Black holes require time to grow, and evidence for them in the early universe remains scarce. Dark matter particles capable of driving reionization would need properties far outside current models. As for those hypothetical megastars, we've never observed anything like them. The reionization puzzle forces us to confront an uncomfortable truth. We might be missing entire chapters of cosmic history, eras where the universe played by rules we don't yet understand. What makes this mystery so pivotal is that reionization wasn't just a cleanup phase, it was the moment the universe became recognizable. Without it, light would still be trapped, galaxies invisible, and the cosmos forever shrouded. The CMB's polarization is our only direct window into this epoch, and its unexpected wrinkles might be the first clues that the early universe was far more complex and far more dramatic than we ever imagined. Buried in the faint whisper of the cosmic microwave background, some researchers believe they've stumbled upon the scars of cosmic strings, hypothetical cracks in space-time left over from the universe's violent birth. These aren't the strings of string theory, but something even stranger: ultra-thin, unimaginably dense filaments of energy, thinner than a proton yet stretching across the cosmos, where the very fabric of reality is twisted like a frayed rope. If they exist, cosmic strings would be relics of a phase transition in the early universe, like cracks forming in ice as it freezes. And according to a handful of controversial studies, their gravitational tug might have left faint but detectable kinks in the CMB's temperature patterns. The hunt for these phantom strings hinges on a peculiar signature: sharp, linear discontinuities in the CMB where temperatures abruptly shift along invisible fault lines. Picture dragging a knife through a painting. The colors on either side wouldn't blend smoothly but would show a stark, razor-straight divide. That's what some teams claim to have spotted in the data. In 2014, a study analyzing Planck satellite observations reported several candidate string signals, including a particularly compelling one near the constellation Eridanus. The catch: these features are so subtle they could just as easily be random noise or artifacts of foreground interference. The implications of cosmic strings, though, are anything but small. If confirmed, they would offer direct evidence of grand unified theories, the idea that all fundamental forces were once merged into a single superforce in the universe's first moments. As the cosmos expanded and cooled, this symmetry might have broken unevenly, leaving behind defects like cosmic strings as cosmic fossils. Some string theory models even suggest these structures could behave like time capsules, encoding information about higher dimensions or the physics of the pre-Big Bang era. Yet the debate rages on. Skeptics argue that the alleged string signatures vanish under closer scrutiny or when analyzing different slices of the CMB data. Without a smoking gun, like a telltale double image of a distant galaxy lensed by a string's extreme gravity, the case remains circumstantial. Alternative explanations, like unlucky alignments of galaxy clusters or instrumental artifacts, can't be ruled out. What makes cosmic strings so tantalizing is their potential to bridge the gap between theory and observation. They might explain anomalies in galaxy distributions or even the origins of supermassive black holes. But until we have irrefutable proof, they linger in the realm of maybe a ghostly possibility etched into the afterglow of creation, waiting for us to unravel their secrets or dismiss them as cosmic mirages. Among the most hotly contested anomalies in the cosmic microwave background are the so-called concentric circles, faint ring-shaped patterns that some researchers claim could rewrite the history of the universe. These circular imprints, first highlighted in 2010 by a team analyzing data from the WMAP satellite, don't match the random fluctuations we'd expect from the Big Bang. Instead, they appear as subtle ripples radiating outward like echoes in a cosmic pond, with temperature variations slightly more pronounced at specific intervals. To those who discovered them, these rings weren't just statistical quirks. They were potential evidence of a cyclic universe, one that has endured multiple Big Bangs. The theory is as radical as it sounds. If the universe cycles through endless expansions and contractions, a model called conformal cyclic cosmology, each previous universe might have left gravitational imprints on the next. These imprints would manifest as concentric circles in the CMB, marking the collision zones of supermassive black holes from an earlier cosmic cycle. Imagine dropping a pebble into water over and over. The overlapping ripples would create nested rings, much like the patterns allegedly found in the CMB. But here's the catch: mainstream cosmologists remain deeply skeptical. When independent teams reanalyzed the data using different statistical methods, many of the reported circles vanished into the noise. Critics argue that the human brain is wired to seek patterns even where none exist, a phenomenon called pareidolia. It's the same tendency that makes us see faces in clouds or animals in star constellations. The Planck satellite, with its higher resolution data, failed to confirm the circles conclusively, leaving the door open for debate. Alternative explanations have emerged. Some suggest these patterns could stem from rare but mundane astrophysical events, like the gravitational lensing of ancient galaxy clusters warping the CMB's light. Others propose they're artifacts of the way we process the CMB's sprawling datasets, where mathematical filters might inadvertently amplify certain geometric shapes. Yet the allure of the circles persists, not just because of their theoretical implications, but because they force us to confront a deeper question. How do we distinguish between genuine cosmic signals and the ghosts of our own assumptions? Whether the circles are real or illusory, their controversy reminds us that the universe's greatest mysteries often lie at the edge of what we're willing to believe. One of the most urgent mysteries in modern cosmology isn't hiding in some distant corner of the universe. It's written into the very expansion of space itself, and the cosmic microwave background is at the heart of the controversy. Scientists call it the Hubble tension, and it's a discrepancy so stark that some are calling it a full-blown crisis. Here's the problem. When we measure how fast the universe is expanding today using nearby galaxies and supernova, we get one number for the Hubble constant, the rate of that expansion. But when we calculate the same number using the CMB's snapshot of the early universe, we get a different value. These two methods, both incredibly precise, disagree by nearly 10%. It's like measuring the speed of a car with two radar guns and getting answers that should be impossible. The implications are enormous. If the CMB's measurement is correct, it suggests the universe is expanding slower than what we see in our local neighborhood. But how could that be? One possibility is that we're missing something fundamental about the physics of the early cosmos. Maybe dark energy, the mysterious force driving cosmic acceleration, isn't constant but changes over time, behaving differently now than it did 14 billion years ago. Some theories propose entirely new particles or forces that briefly altered the expansion rate in the universe's infancy, leaving the CMB with a memory of a slower pace. Others suggest that exotic forms of dark matter or unexpected interactions between matter and radiation could have tweaked the early universe's dynamics in ways we haven't accounted for. Yet skeptics argue the tension might not signal new physics at all, just hidden errors in our measurements. Local observations rely on complex distance ladders, where each rung from Cepheid variable stars to Type Ia supernova could introduce tiny inaccuracies that snowball into the discrepancy we see. On the flip side, the CMB's Hubble constant is derived from a chain of assumptions about cosmic inflation, dark matter, and the universe's geometry. If any of those are subtly wrong, the whole calculation could be off. The debate has grown so heated that some researchers are now questioning foundational pillars of cosmology, like whether our universe is perfectly flat or if dark energy's properties are stranger than we thought. What makes this mystery so gripping is that it forces us to confront the limits of our knowledge. If the Hubble tension is real, if the universe's expansion rate genuinely differs between then and now, it would mean our cosmic timeline is missing a crucial chapter. But if it's an illusion, it exposes how fragile our understanding might be, built on assumptions we've yet to test fully. The answer, whatever it is, won't just resolve a number, it could redefine the story of everything. And until we know for sure, the tension keeps pulling at the seams of cosmology itself. Deep within the cosmic microwave background lies an invisible tug of war, one that pits the universe's oldest light against the ghostly particles known as neutrinos. These elusive, nearly massless particles flood the cosmos, trillions passing through your body every second without a trace. Yet despite their ethereal nature, neutrinos wield surprising influence. The CMB's delicate temperature patterns bear their fingerprints, revealing how these cosmic specters shaped the early universe's structure. But here's where things get weird. The mass of neutrinos inferred from the CMB doesn't quite match what particle physics experiments on Earth suggest. It's as if the universe is telling one story about these particles, while our detectors whisper another. The discrepancy hinges on a deceptively simple question: how much do neutrinos actually weigh? The standard model of particle physics long assumed they were massless, but experiments like Super Kamiok and proved otherwise. Neutrinos oscillate between different types, a behavior only possible if they have mass. Yet pinning down that mass has been maddeningly difficult. Earth-based experiments which track neutrino oscillations over short distances suggest the combined mass of all three known neutrino types should be at least 6/10 of an electron volt. But when cosmologists analyze the CMB, they get a different answer. The way neutrinos suppress the growth of cosmic structures like galaxies and clusters in the early universe points to a far lighter total, likely under 3/10 of an electron volt. This gap might seem trivial, but in the high-stakes world of particle physics, it's a chasm. One explanation could lurk in the shadows of the standard model, sterile neutrinos. These hypothetical particles wouldn't interact via any known force except gravity, making them invisible to our detectors. Yet if they exist, they'd subtly alter how ordinary neutrinos oscillate and cluster, potentially bridging the divide between lab results and cosmic observations. Another possibility is that neutrinos aren't the only lightweight particles leaving their mark. Some theories propose undiscovered, dark radiation, relatives of neutrinos that pervaded the early universe, skewing the CMB's signals in ways we're only beginning to untangle. The stakes here extend far beyond neutrino masses. If the CMB's constraints hold, they might hint at physics beyond the standard model, particles or forces that shaped the universe before the first stars flickered to life. Alternatively, if terrestrial experiments win out, it could mean our models of cosmic structure formation are missing a crucial ingredient. Either way, the neutrino mass anomaly isn't just a technical hiccup. It's a rare collision between the infinitesimally small and the unimaginably vast, where the physics of subatomic particles meets the architecture of the cosmos itself. And until we solve it, we're left with a haunting question. Are we measuring neutrinos wrong, or is the universe hiding something even stranger? Hidden in the cosmic silence of the cosmic microwave background is an absence so profound, it threatens to reshape our understanding of the universe's earliest moments, the missing fingerprints of magnetic monopoles. These hypothetical particles are the universe's unmatched socks, single magnetic poles that should exist if grand unified theories are correct, yet nowhere to be found. According to these theories, in the searing heat of the cosmos's first fraction of a second, the fundamental forces electromagnetism, the strong force, the weak force were one and the same. As the universe expanded and cooled, this symmetry shattered, leaving behind defects in spacetime. Just as cracks form when water freezes into ice, these defects should have birthed magnetic monopoles particles with only a north or south pole, unlike the paired poles of every magnet we've ever seen. But the CMB tells a different story. If monopoles were as abundant as theory predicts, they would have left glaring distortions in the CMB's temperature patterns, hotspots, or strange polarization signals where their massive energy warped spacetime. Instead, we find nothing, no anomalous bumps, no telltale swirls. It's as if someone erased a crucial character from the cosmic story without leaving a trace. This paradox, called the monopole problem, has haunted physicists since the 1970s, when theorists first realized just how many of these particles should exist. If the math is right, the early universe would have produced enough monopoles to outnumber atoms, turning the cosmos into a dense soup of magnetic oddities. Clearly, that's not the case, so where did all the monopoles go? One solution, cosmic inflation, suggests the universe expanded so rapidly in its first moments that it diluted monopoles beyond detection, scattering them so thinly that their average density today would be nearly zero. It's a neat fix, but it comes with baggage. If inflation smoothed away monopoles, why didn't it erase all primordial irregularities, leaving the CMB perfectly uniform? The fact that we see any fluctuations at all means inflation had to be exquisitely fine-tuned, a lucky coincidence that strains credulity. Others argue that monopoles might still exist, but in a form we can't detect. Some theories propose they clustered into invisible monopole nuggets, hiding in the voids between galaxies. More radical ideas suggest monopoles decayed into other particles long ago, vanishing into the quantum foam. Then there's the unsettling possibility that grand unified theories are simply wrong, that magnetic monopoles never existed and we've been chasing a phantom. The silence of the CMB on this issue is deafening. It forces us to question not just the physics of the early universe, but the very nature of symmetry breaking, the process that gave rise to the forces we know today. If monopoles aren't there, what other surprises might be lurking in the cosmic shadows? The answer, or lack thereof, could rewrite the rules of particle physics, or reveal a universe far stranger than we ever predicted. The cosmic microwave background should be the same in every direction, a uniform glow from the dawn of time. But when scientists mapped its temperature across the sky, they found something unsettling. One half of the universe appears ever so slightly warmer than the other. This odd mismatch, known as the dipole asymmetry, is like discovering that the ocean's surface is just a fraction hotter on one side of the planet for no apparent reason. At first glance, the explanation seems simple. Our solar system is moving through space, and that motion should create a Doppler-like shift in the CMB, making light appear warmer in the direction we're heading and cooler behind us. But here's where things get strange. When we subtract this expected motion, the asymmetry doesn't vanish entirely. A stubborn imbalance remains, as if the early universe itself was lopsided. This anomaly isn't just a statistical blip. The CMB's dipole asymmetry stretches across vast swaths of the sky, with one hemisphere consistently measuring about 1 part in 1,000 warmer than its opposite. The odds of such a pattern arising randomly, less than 1 in 10,000. So if our local motion doesn't fully account for it, what's left? One possibility is that we're seeing the gravitational tug of something enormous beyond the observable universe, a structure so vast its pull distorts the CMB like a hidden hand tilting the cosmic scales. Imagine standing in a valley and feeling a breeze you can't explain, only to realize it's being funneled by a mountain just beyond the horizon. Yet even this explanation raises thorny questions. The sheer scale of such a structure would defy our understanding of cosmic inflation, which predicts a relatively uniform distribution of matter on the largest scales. Alternative theories suggest the asymmetry might be a relic of pre-inflationary physics, a scar from processes that operated before the Big Bang as we know it. Some models propose that quantum fluctuations in the very early universe weren't perfectly random, leaving behind subtle imbalances that froze into the CMB. Others speculate about exotic topologies like a universe that loops back on itself in ways that amplify certain directions, the most radical interpretation. That the dipole asymmetry isn't a flaw in our observations but a clue that the universe itself is fundamentally anisotropic, that the laws of physics might vary slightly depending on which way you look. This idea, though controversial, isn't entirely far-fetched. Certain variations of string theory allow for directional dependencies in nature's constants, meaning the cosmos could have a preferred orientation we've only just begun to notice. What makes this mystery so tantalizing is that it sits at the crossroads of the observable and the speculative. If the asymmetry is purely local, it challenges our measurements. If it's primordial, it challenges our theories. Either way, the CMB's uneven glow forces us to confront an unsettling truth. The universe might not be as directionless as we thought, and its secrets could be hiding in plain sight, written in the faintest variations of ancient light. The cosmic microwave background's temperature fluctuations are supposed to follow a predictable statistical pattern, what scientists call a Gaussian distribution. Think of it like rolling dice. While any single outcome is random, over time the results should cluster around certain probabilities in a bell curve. But what if the CMB's dice are loaded? A growing number of studies suggest that some of its fluctuations might deviate from this expected randomness, displaying what's known as non-Gaussianity. These subtle anomalies, if real, could be cracks in the foundation of our cosmic models, hinting at forces or phenomena that operated in the universe's first moments, long before particles or light even existed. At first glance, the idea seems abstract, but the implications are profound. Standard inflation theory predicts the CMB's fluctuations should be almost perfectly Gaussian, a consequence of quantum noise stretched to cosmic scales during the universe's rapid expansion. Yet when researchers analyze high-precision data from satellites like Planck, they find faint but persistent deviations, slight skews or clumping in the temperature patterns that don't quite fit the mold. Some regions of the CMB appear marginally hotter or colder than pure chance would allow, as if an unseen hand had nudged the cosmic dice during the Big Bang. The hunt for non-Gaussianity is like searching for fingerprints on a snowflake, extraordinarily delicate. Some of the earliest claims stemmed from unusual hotspots or asymmetrical distributions in the CMB's multipole moments, while others pointed to strange alignments between large-scale temperature patterns. Skeptics argue these could be artifacts of foreground contamination or statistical flukes, but the anomalies keep resurfacing in independent analyses. If they're not noise, what could explain them? One leading theory involves modifications to inflation itself. Maybe the universe's expansion wasn't as smooth as we've assumed. Certain models of multi-field inflation propose that multiple exotic particles or energy fields interacted chaotically during the universe's birth, imprinting non-Gaussian ripples onto spacetime. Others suggest that primordial magnetic fields or cosmic strings, those hypothetical spacetime defects, might have twisted the CMB's fluctuations into unexpected shapes. Even wilder ideas, like collisions between bubble universes in a multiverse, could leave behind telltale non-Gaussian signatures. Yet the plot thickens when we consider alternative explanations closer to home. Could our Milky Way's own magnetic field or dust emissions subtly bias the data? Some researchers contend that even the most careful foreground subtraction might miss faint distortions, especially at large angular scales where non-Gaussian signals seem strongest. Others point to the limitations of our statistical tools, human-designed algorithms that might inadvertently amplify certain patterns while filtering out others. The debate is far from settled, but the stakes couldn't be higher. Confirmed non-Gaussianity wouldn't just tweak our models, it could shatter them, forcing us to rewrite the story of cosmic dawn. Whether the signal is real or illusory, its pursuit is already reshaping how we probe the universe's origins. And that's the heart of this mystery. Sometimes the smallest deviations in the data whisper the loudest secrets about reality itself. Perhaps no cosmic mystery exposes the gaps in our understanding like the enigma of early dark energy, a hypothetical force that might have briefly surged through the universe before vanishing without a trace. The idea emerged as a desperate fix for some of the CMB's most stubborn puzzles, from the Hubble tension to anomalies in large-scale structure formation. Picture this: in the universe's first few 100,000 years, an extra dose of dark energy distinct from the kind accelerating today's expansion flared up, pushing space apart faster than expected. Then, just as suddenly, it faded, leaving behind only subtle wrinkles in the CMB as evidence. It's a cosmic sleight of hand that could explain why our two methods of measuring the universe's expansion disagree so dramatically. The appeal of early dark energy lies in its surgical precision. By tweaking the rate of cosmic expansion during a narrow window of time, it could reconcile the CMB's predictions with observations of nearby galaxies without appending the rest of cosmology. The math is elegant. This transient burst of energy would have altered how sound waves propagated through the primordial plasma, subtly shifting the CMB's acoustic peaks to better match what we measure today. It's like adding a single dash of spice to a recipe, just enough to balance the flavors without overwhelming the dish. But here's where Occam's razor starts to tremble. Introducing an entirely new form of energy, one that operates on a schedule we can't yet explain, feels perilously close to inventing a cosmic deus ex machina. Critics argue that early dark energy risks becoming a fix-all crutch, a theoretical band-aid slapped onto every anomaly until the model becomes too convoluted to test. After all, science thrives on simplicity, and adding invisible entities to patch observational gaps is a slippery slope. Remember the ether? 19th century physicists invented it to explain light's propagation, only for Einstein to later render it obsolete with relativity. Could early dark energy be a similar placeholder, masking a deeper truth we've yet to uncover? Proponents counter that sometimes the universe is messy, and clinging to simplicity for its own sake might blind us to reality's complexities. They point to other successful theories that initially seemed contrived, like inflation itself, an idea once viewed as speculative but now a cornerstone of cosmology. And intriguingly, early dark energy isn't entirely untethered from theory. Certain string theory models predict extra dimensions or scalar fields that could manifest as transient dark energy, flickering in and out of existence during the universe's infancy. The real test, though, lies in the data. Future CMB experiments, like the upcoming CMB S4 project, could hunt for the unique imprint early dark energy would leave on polarization patterns. Alternatively, galaxy surveys might uncover unexpected voids or clusters in large-scale structure footprints of that brief, violent push. Until then, the hypothesis lingers in a quantum superposition of plausibility, neither confirmed nor debunked, but hovering tantalizingly at the edge of discovery. Whether it's a stroke of genius or a dead end, one thing is certain: the universe rarely surrenders its secrets without a fight. Among the most elusive ghosts haunting the cosmic microwave background are the so-called B modes, a subtle twist in its polarization patterns that could reveal the universe's very first tremors. These faint swirls, if detected, would be the smoking gun for primordial gravitational waves, ripples in spacetime itself, set in motion during the violent expansion of cosmic inflation. The theory seemed airtight. Just as a boat leaves ripples in water, inflation should have stirred gravitational waves into the fabric of reality, imprinting a telltale curl onto the CMB's light. Yet after decades of hunting with increasingly sensitive telescopes from Bicep to Planck, these B modes remain conspicuously absent. It's as if the universe forgot to leave behind one of its most critical pieces of evidence. The absence of B modes isn't just a technical hiccup, it's a potential crisis for inflation. The simplest versions of the theory predict gravitational waves strong enough to produce detectable B mode polarization, especially at large angular scales where inflation's fingerprint should be clearest. But the data tells a different story. While B modes have been found, they're almost entirely due to mundane sources like interstellar dust or gravitational lensing, not primordial waves. The primordial signal, if it exists at all, is drowned out by noise. This forces physicists to confront an awkward question. Did inflation happen differently than we thought, or are we chasing a phantom? One camp argues the lack of B modes simply means inflation was gentler than expected. Perhaps the energy scale of inflation was lower, producing gravitational waves too weak for current telescopes to spot. This wouldn't kill the theory, just narrow its possibilities, like realizing a storm you thought was a hurricane was merely a strong wind. Other researchers propose more radical fixes. Could inflation have been single field, driven by just one quantum energy source, which naturally suppresses gravitational wave production? Or might the universe have undergone a warm inflation, where particles interacted so fiercely during expansion that gravitational waves were smothered before they could grow? Then there's the nuclear option, that inflation never happened at all. A handful of theorists suggest alternatives like bouncing cosmologies, where the universe cycles through contractions and rebounds, or emergent universes that condense from a timeless void. These ideas predict no primordial B modes at all, a clean fix for their absence, but at the cost of discarding one of cosmology's most successful frameworks. The stakes here are existential. Without B modes, we lose our only direct window into the universe's first trillionth of a second, a time so remote that even protons and electrons hadn't yet formed. Amid the debate, a third possibility lingers, that we're not looking hard enough. Future telescopes like the Simons Observatory or Light Bird aim to probe deeper into the CMB's polarization, hunting for B modes at frequencies where dust interference fades. But until then, the silence speaks volumes. Whether the missing B modes point to tweaked inflation, its demise, or our own observational limits, one thing is clear. The cosmos is still holding its cards close, leaving us to wonder if the universe's first moments were quieter or far stranger than we ever imagined. The cosmic microwave background doesn't just carry the imprint of the early universe. It also holds a distorted reflection of everything that's happened since, warped by the gravitational pull of matter lying between us and the CMB's ancient light. This distortion, called gravitational lensing, acts like a cosmic funhouse mirror, bending and magnifying the CMB's patterns as they travel across billions of light years. Normally, this lensing should follow predictable rules, its strength determined by the clumpiness of dark matter and the geometry of spacetime. But when scientists measured it, they stumbled upon a baffling discrepancy. The lensing effect is stronger than our models say it should be, as if invisible hands are tugging at the fabric of reality harder than we ever anticipated. This anomaly isn't just a minor statistical blip. The excess lensing shows up consistently across multiple datasets, from the Planck satellite to ground-based telescopes like the Atacama Cosmology telescope. It's as if the universe's matter is clustered more tightly than expected, creating deeper gravitational wells that bend light more sharply. One possible explanation points to dark matter behaving in ways we haven't accounted for. Maybe it's clumpier on large scales, forming denser filaments and halos that amplify lensing. Or perhaps dark matter interacts with itself through unknown forces, adding extra gravitational, sticking power that pulls structures together faster than standard cosmology predicts. Yet dark matter might not be the only culprit. Alternative theories suggest the anomaly could stem from something even more profound, a flaw in our understanding of gravity itself. Modified Newtonian dynamics, or MND, proposes tweaks to gravity's rules on cosmic scales, eliminating the need for dark matter altogether. While MND struggles to explain all cosmological observations, some variants predict just the kind of enhanced lensing we're seeing in the CMB. Then there's the wild card, early dark energy. If a burst of exotic energy surged through the universe before fading, it could have altered how structures formed, leaving behind a lensing signal that looks unnaturally strong today. The implications ripple far beyond the CMB. If dark matter is clumpier, it could reshape how galaxies form and evolve. If gravity is stranger, it would rewrite the rules governing the cosmos. And if early dark energy is the answer, it means the universe's expansion history is far more dramatic than we've assumed. Future telescopes like the Vera C. Rubin Observatory aim to map dark matter's distribution with unprecedented precision, potentially solving the riddle. But until then, the CMB's anomalous lensing stands as a silent challenge, a cosmic hall of mirrors where reflections bend just enough to hint that something, somewhere in our models, is not quite as it seems. The cosmic microwave background is often described as a near-perfect blackbody, a thermal echo so pristine it follows the laws of radiation with almost mathematical precision. But what if it isn't as perfect as we think? Tucked within its spectrum could lie faint distortions, subtle deviations from that ideal curve, hinting at moments when the early universe was jolted by bursts of energy we've yet to explain. Scientists call these spectral distortions, and they come in two main flavors, mu distortions and Y distortions. The mu type, in particular, is like a cosmic breadcrumb evidence of energy injections that occurred between about 100,000 and 1 million years after the Big Bang, a period when the universe was too young for stars but too old for the primordial plasma to simply absorb excess energy without a trace. These distortions should exist. Theory predicts that violent events collapsing cosmic strings, evaporating black holes, or even the decay of exotic particles would have dumped energy into the early cosmos, heating the CMB's photons in ways that leave telltale kinks in their spectrum. Yet when we search for mu distortions, the data comes back suspiciously clean. It's as if the universe underwent its turbulent infancy without leaving a single fingerprint on the one piece of evidence we expected to bear its marks. This absence isn't just puzzling, it's borderline paradoxical. If the early universe was as dynamic as we believe, where are the scars? One possibility is that our instruments simply aren't sensitive enough. Detecting mu distortions requires measuring the CMB spectrum with precision down to 1 part in a billion, a task so delicate that even the slightest interference from galactic dust or instrument noise can swamp the signal. Projects like the proposed Pixie satellite aim to hunt for these distortions with unprecedented accuracy, but for now we're left with an unsettling quiet. Another explanation is more radical. Maybe the energy injections never happened, or happened in ways we haven't imagined. Could the universe have cooled more uniformly than our models suggest, with no room for violent disruptions? Or might the energy have been absorbed by something other than photons, perhaps an unknown form of dark matter or hidden fields that interacted selectively with the early plasma? Some theorists even speculate about dark photons, particles that could have siphoned energy away from the visible universe, leaving the CMB unnaturally smooth. The stakes here extend far beyond academic curiosity. If mu distortions exist but elude us, they could pinpoint the exact moments when exotic physics dominated the cosmos. If they're truly absent, it might mean rewriting our timelines of cosmic evolution, erasing events we thought were inevitable. Either way, their silence is a mystery that refuses to stay quiet, a cosmic whisper urging us to listen harder, to build better tools, and to question whether the early universe was as chaotic as we've assumed, or if its calm surface hides depths we've yet to fathom. Some of the most tantalizing whispers hidden in the cosmic microwave background might be the faint echoes of quantum gravity, a theory that has eluded scientists for over a century. At the heart of this enigma lies a fundamental contradiction. Einstein's general relativity describes gravity as the curvature of spacetime on cosmic scales, while quantum mechanics governs the chaotic dance of particles at the subatomic level. Yet these two frameworks refuse to unite, leaving a glaring gap in our understanding of reality. The CMB, with its pristine snapshot of the universe's infancy, could be the Rosetta Stone that finally deciphers their connection. Imagine the universe in its first moments, a seething quantum foam where spacetime itself flickered in and out of existence. Under such extreme conditions, gravity wouldn't behave as the smooth force we know today. Instead, it would become granular, quantized, governed by rules we've yet to uncover. These quantum gravitational tremors, if they existed, could have left subtle scars on the CMB's temperature patterns, like fingerprints on an ancient artifact. But where do we look for them? One promising avenue lies in the way the CMB's fluctuations deviate from perfect randomness. Certain anomalies, whether the axis of evil, the missing large-scale power, or non-Gaussian skews, might not be mere statistical flukes. They could be artifacts of spacetime's underlying quantum structure, imprinted before inflation smoothed the cosmos into the universe we recognize. Loop quantum cosmology, a leading candidate for quantum gravity, offers a compelling framework. This theory suggests that spacetime isn't infinitely divisible but woven from tiny, discrete loops. Think of a fabric made of microscopic threads. In this model, the Big Bang wasn't a singularity but a big bounce, where a previous universe collapsed before rebounding into ours. If correct, this bouncing process would have left distinctive signatures in the CMB's polarization patterns, potentially explaining anomalies like the unexpected lack of power at large scales. Supporters point to tentative hints in the data, subtle correlations between temperature fluctuations that defy classical predictions, but the evidence remains controversial. Even more radical is the holographic principle, which posits that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface at its boundary. If true, the CMB could be a kind of cosmic hologram, its fluctuations mirroring quantum entanglement patterns on this unseen edge. Some researchers argue that certain statistical asymmetries in the CMB's temperature maps align eerily well with holographic predictions, as if the universe is subtly revealing its true, lower-dimensional nature. Yet for all their elegance, these theories face formidable challenges. Quantum gravity operates at energies trillions of times higher than what our particle colliders can reach, leaving the CMB as one of the few observational windows we have. The signals, if they exist, are buried under layers of cosmic noise, requiring precision measurements beyond today's technology. Future missions like CMB S4 or space-based interferometers might finally detect the telltale swirls of primordial gravitational waves or the statistical fingerprints of spacetime's quantum grain. Until then, the CMB's quiet anomalies continue to taunt us, hinting that the answers to gravity's deepest secrets may have been written in the sky all along, waiting for us to learn how to read them. One of the strangest claims about the cosmic microwave background is that it might not be as static as we've assumed, that this ancient light could be subtly shifting over time, defying its reputation as a fossilized echo of the Big Bang. For decades, scientists have treated the CMB as the ultimate cosmic constant, its patterns locked in place 13.8 billion years ago. But a handful of researchers argue we might be missing something far more dramatic, evidence that the universe itself is still evolving in ways we don't understand. The idea first gained traction when a team analyzing data from the WMAP satellite noticed peculiar discrepancies between observations taken years apart. Certain temperature fluctuations appeared to shift slightly, as if the CMB's frozen snapshot was actually a slow-motion film. Mainstream cosmologists dismissed the findings as statistical noise or calibration errors, but the whispers persisted. When the Planck satellite's higher-resolution data also hinted at similar anomalies, tiny but measurable drifts in the CMB's dipole and quadrupole moments, even skeptics had to pause. Could the universe's oldest light truly be changing, or are we seeing ghosts in the data? Explaining such variability would require rewriting physics as we know it. If the CMB isn't static, it could mean the constants governing our universe, like the speed of light or the strength of gravity, aren't constants at all. Some fringe theories propose that spacetime itself is gradually stretching or warping on cosmic scales, altering how we perceive the CMB's ancient photons as they travel to us. Others suggest we're witnessing the gravitational influence of parallel universes brushing against our own, their unseen mass subtly warping the CMB over time. The most radical hypothesis, that our universe is caught in a slow-motion collision with another bubble universe, its boundary vibrations imprinting gradual changes onto the CMB like ripples spreading across a pond. Yet the simplest explanation remains the most likely: human error, subtle shifts in instrument sensitivity, unnoticed foreground interference from galactic dust, or even the way we process raw data could mimic the illusion of a dynamic CMB. The Planck team's exhaustive checks found no conclusive evidence of time variation, and most researchers argue that extraordinary claims demand extraordinary proof we simply don't have. Still, the possibility lingers like a shadow at the edge of cosmology, a reminder that even our most steadfast assumptions about the universe might one day be upended. What makes this mystery so captivating isn't just the science, it's the philosophical stakes. If the CMB is changing, it implies a universe far more alive, far more restless than we've ever imagined. Time itself might not be the steady river we think it is, but something stranger, flowing in ways we've yet to comprehend. Until we have irrefutable evidence, the question remains open, dangling between radical reinvention and the quiet patience of scientific rigor. The CMB has always been a message from the past, but what if it's also trying to tell us something about the present? Among the most provocative theories to emerge from the cosmic microwave background's anomalies is the spine-tingling possibility that these irregularities aren't random quirks, but glitches in a simulated reality. Picture this: our universe might be an unfathomably advanced computer program, and the CMB's oddities, like the axis of evil or the missing large-scale fluctuations, could be tiny coding errors, artifacts of imperfect rendering at the edges of the simulation's processing power. It's a concept straight out of science fiction, yet some physicists and philosophers argue it's worth taking seriously, if only as a thought experiment. The logic hinges on a simple premise: if a civilization could one day create hyper-realistic simulations of conscious beings, the statistical likelihood that we're living in the original universe diminishes. Proponents point to the CMB's anomalies as potential evidence, like pixels repeating in a video game or the uncanny alignment of temperature patterns resembling a forced optimization to save computational resources. The cold spot, for instance, might not be a collision with another universe but a memory buffer overflow, a place where the simulation struggled to render details smoothly. Even the CMB's eerie uniformity could reflect a developer's choice to simplify initial conditions, avoiding the processing nightmare of infinite variability. But before we rewrite cosmology as a digital artifact, Occam's razor slices through the speculation. The simulation hypothesis, while mesmerizing, demands layers of unprovable assumptions, not just about the nature of reality, but about the motivations and constraints of hypothetical programmers. Why would they leave glitches visible? Wouldn't a civilization capable of such a simulation also have the power to debug it? Scientific skeptics argue that invoking a simulation to explain CMB anomalies is like blaming ghosts for flickering lights. It might feel satisfying, but it doesn't actually advance our understanding of the wiring. Yet the debate isn't entirely fruitless. The simulation idea forces us to confront how we distinguish between natural randomness and engineered patterns. After all, the CMB should be statistically isotropic. So when we see anomalies, the real question isn't, are we in a simulation? But what natural processes could break symmetry in these precise ways? Some physicists suggest that focusing on the simulation analogy might ironically lead us to real physics, like how early chemists borrowed mythological metaphors to explain reactions before uncovering molecular truth. The irony is delicious. Even if the universe isn't a simulation, treating it like one could still help us crack its code. Maybe the cold spot isn't a rendering error but a clue about quantum entanglement at cosmic scales. Perhaps the axis of evil isn't a programming shortcut but evidence of a pre-Big Bang phase we've yet to model. The simulation hypothesis, for all its spectacle, ultimately mirrors science's oldest impulse to question whether the patterns we see are accidents or messages. And until we know for sure, the CMB's anomalies will keep us wondering. Are we decoding the universe's deepest laws or just reading the lines of someone else's script? Right now, the cosmic microwave background is the oldest light we can see, a whisper from the dawn of time. But even echoes fade. Over trillions of years, as the universe expands faster and faster, this relic glow will stretch into longer, weaker wavelengths, its photons pulled thin by the relentless tug of dark energy. What began as visible light will shift to infrared, then to radio waves, and finally into undetectable ripples lost in the void. The CMB won't vanish abruptly. It will dissolve like ink dispersing in an infinite ocean, until even the most advanced instruments of future civilizations strain to find its trace. Imagine a time so far ahead that stars have burned out, galaxies have drifted beyond each other's horizons, and the night sky is pitch black. Any beings alive, then machines, post-biological intelligences, or something we can't fathom, might stumble upon this near-invisible remnant and face a puzzle with missing pieces. Without the context we have today, would they recognize the CMB as a relic of creation? Or would its faint, distorted signals seem like cosmic static, a mystery without an answer? There's a haunting irony here. The CMB is our Rosetta Stone for decoding the universe's origins, yet its own fate is to become indecipherable. Future astronomers might detect a uniform, near-zero temperature and assume the cosmos always existed in this cold, empty state, unaware of the fiery birth it once revealed. The very evidence that taught us about the Big Bang will one day hide it, but perhaps the story doesn't end there. Some theories suggest that in a trillion years, quantum fluctuations might spawn new universes in the vacuum. If so, the CMB's fading glow could be the last ember of our cosmos before a new fire ignites. Or maybe intelligent life will find ways to preserve this knowledge, carving it into indestructible monuments or encoding it in timeless quantum structures. For now, though, we're the lucky ones. We live in the brief cosmic moment when the CMB is still clear enough to read, like finding a message in a bottle just before the tide washes it away. Its impending disappearance isn't just a footnote in astrophysics, it's a reminder that the universe is always changing, and some truths are only visible for a while. So we keep listening, decoding, and marveling at the light that's been traveling for almost 14 billion years, because one day it will simply be gone. The cosmic microwave background's strangest anomalies don't just hint at unknown physics. They might be our first glimpse beyond the edge of reality itself, into a multiverse teeming with unseen universes. Take the cold spot, that eerie billion-light-year stretch of unnaturally chilled space. To some theorists, this isn't just a cosmic curiosity, it's a bruise. A collision mark where our universe may have bumped against another bubble in an infinite foam of parallel realities during the chaotic frenzy of eternal inflation. Eternal inflation, the leading multiverse theory, paints a dizzying picture. Our Big Bang wasn't unique, but one of countless explosions in an ever-expanding quantum foam. Each bubble universe cools into its own reality with different physical laws, forever out of reach unless they occasionally brush against each other. The cold spot's temperature dip matches simulations of such a collision, where another universe's gravity subtly tugged on ours, leaving a gravitational shadow in the CMB. But here's where the debate ignites. Skeptics counter that supervoid's vast, mostly empty regions of space could mimic the cold spot's signature without invoking other universes. Yet even the largest known supervoids can't fully account for its extreme chill, leaving the door cracked for wilder possibilities. The multiverse argument gains traction when paired with other symbiodities. The axis of evil's peculiar alignments, for instance, might reflect pre-inflationary structures, ancient imprints from a parent universe that birthed ours. Some models suggest these patterns could be echoes of quantum entanglement between our universe and its neighbors, frozen into the CMB when inflation ended. Meanwhile, the missing large-scale fluctuations fit neatly with predictions that our observable universe is just a tiny patch of a vaster cosmos, where statistical variations smooth out across infinite space. But multiverse theories come with heavy baggage. Critics argue they're untestable by nature. If other universes are permanently inaccessible, how can we ever confirm they exist? The cold spot might be intriguing, but it's hardly proof when mundane explanations, however incomplete, remain possible. Even proponents admit eternal inflation has a fudge factor problem. It can predict almost any observation by tweaking parameters, making it frustratingly unfalsifiable. As Nobel laureate David Gross quipped, a theory that predicts everything predicts nothing. Yet the allure persists because the alternatives can be just as radical. If the CMB anomalies aren't multiverse fingerprints, they might point to something equally unsettling: that our universe is fundamentally anisotropic, with physics that vary by direction. Or worse, that we've misunderstood inflation entirely, and the cosmos began under rules we haven't yet imagined. Whether the cold spot is a cosmic crash site or a statistical mirage, one truth remains: the CMB isn't just a relic of our universe's birth. It's a mirror reflecting the most profound question of all: are we alone in existence, or is our reality just one note in an infinite symphony? For all its cosmic grandeur, the cosmic microwave background is frustratingly faint, a whisper buried under layers of interference that push our technology to its limits. Every anomaly we detect, from the cold spot to the axis of evil, must first be disentangled from a cacophony of noise: the microwave hum of our own galaxy's dust, the afterglow of distant quasars, even the subtle warmth of Earth's atmosphere bleeding into telescope readings. Some of the CMB's most controversial oddities might not be cosmic at all, but artifacts of the very tools we use to observe them. Take instrumental noise, the unavoidable hiss of electronics in telescopes like Planck or WMAP. Even the most advanced detectors generate minute errors, and when you're measuring temperature variations as tiny as 1 part in 100,000, those errors can mimic false signals. Statisticians call this "look elsewhere" effect. Scour enough data, and random noise will inevitably arrange itself into patterns that look meaningful. The cold spot, for instance, might simply be the universe's version of seeing faces in static, a fluke amplified by our eagerness to find significance in chaos. Foreground contamination is another silent saboteur. our Milky Way's sprawling dust clouds emit microwaves that blend seamlessly with the CMB's primordial glow. Though scientists painstakingly subtract these foregrounds using complex algorithms, residuals linger like smudges on a lens, the much-debated concentric circles in the CMB. Some researchers argue they're nothing more than the ghostly imprint of interstellar dust filaments, their spiral structures misinterpreted as cosmic echoes. Even the dipole asymmetry, that lopsided warmth in one hemisphere, could reflect unaccounted emissions from galaxy clusters or the Sunyaev-Zeldovich effect, where hot gas distorts CMB photons as they pass through. Then there's the thorniest issue of all, confirmation bias. Humans are pattern-seeking creatures, and cosmologists are no exception. When a team announces a discovery, say gravitational wave B modes, it's tempting to interpret subsequent data through that lens, overlooking alternative explanations. The infamous Bicep 2 incident in 2014 serves as a cautionary tale. Researchers initially claimed a detection of primordial B modes, only to later realize galactic dust had fooled them. The episode underscores a brutal truth. In CMB science, the line between breakthrough and blunder is often thinner than a photon's wavelength, but hope isn't lost. A new generation of telescopes, like the upcoming CMB-S4, promises to cut through the noise with unprecedented precision. With 10 times the sensitivity of Planck and detectors buried under the pristine ice of the South Pole to shield against atmospheric interference, CMB-S4 could finally settle debates like the Hubble tension or the reality of cosmic strings. Meanwhile, space-based missions like LightBird aim to map the CMB's polarization in frequencies where dust emissions fade, isolating the true primordial signal. These aren't just incremental upgrades, they're quantum leaps, offering the equivalent of switching from a grayscale TV to Ultra HD. Yet even with perfect data, mysteries will persist. The universe's oldest light will always be a palimpsest, its deepest truths written over by eons of cosmic history. What we dismiss as noise today might tomorrow reveal itself as a message, one we're only beginning to decode. The real lesson isn't that our instruments are flawed, but that the cosmos demands humility. Every anomaly, whether artifact or revelation, reminds us that discovery isn't just about seeing farther, it's about learning how to see clearly. The deeper we probe the cosmic microwave background's enigmas, the more we're forced to confront a humbling truth. The universe might not just be stranger than we imagine, but stranger than we can imagine. Every anomaly, the cold spot, the axis of evil, the missing B modes, isn't just a puzzle to solve. It's a mirror reflecting the limits of human comprehension. For centuries, we've crafted elegant theories to explain the cosmos, from Newton's clockwork mechanics to Einstein's warped spacetime. Yet the CMB whispers that our models, however brilliant, might only be rough sketches of a far grander masterpiece. Consider what's at stake. If the CMB's irregularities stem from a multiverse, it would mean our universe is one bubble in an infinite froth of realities, each with its own laws of physics. Suddenly, the fine-tuning of our cosmos, the improbable constants that allow stars, planets, and life to exist, wouldn't be miraculous, just statistically inevitable. We'd be living in the lottery ticket that happened to win. But if the anomalies instead reveal flaws in our understanding of gravity or quantum mechanics, it could mean the theory of everything we've sought for decades is still out of reach, waiting in the shadows of undiscovered physics. This tension between revelation and mystery defines our cosmic moment. On one hand, the CMB has given us unprecedented clarity, confirming the Big Bang, mapping dark matter, and even hinting at inflation's existence. On the other, it's peppered with gaps that resist explanation, like a manuscript with crucial pages torn out. The philosopher in us might ask, is this how the universe works, or just how it appears to beings like us, bound by 3 dimensions and finite senses? Imagine ants analyzing a Picasso. Their 2-dimensional worldview could never grasp the artist's intent. Are we, in our quest for cosmic truths, just as limited? There's a poignant beauty in this uncertainty. The CMB's mysteries remind us that science isn't just about answers. It's about the thrill of the hunt, the humility of knowing some questions might outlast our species. The cold spot could vanish under better data tomorrow, or it might bloom into evidence of parallel worlds. The Hubble tension might resolve into a calibration error, or crack open a new chapter in dark energy's story. This dance between knowing and not knowing is what makes cosmology alive, urgent, and profoundly human. Perhaps the greatest lesson buried in the CMB's Afterglow is this: the universe owes us no clarity. Its secrets aren't designed for our comprehension, yet here we are, a flicker of consciousness in an ancient cosmos, piecing together whispers from the dawn of time. Whether we're decoding a multiverse or staring at the edge of a mathematical abyss, the act of searching itself is what defines our place in the cosmos, not as passive observers, but as storytellers weaving meaning from the light of a dying fire. From the eerie uniformity of the cosmic microwave background to the unsettling depths of its missing B modes, these 25 mysteries aren't just gaps in our knowledge. They're reminders of how much we still don't understand about the cosmos. The CMB was supposed to be the ultimate decoder ring, a pristine relic revealing the universe's birth certificate. Instead, it's handed us a riddle wrapped in an enigma, each anomaly whispering questions we can't yet answer. Why is one half of the sky subtly warmer than the other? What carved that colossal cold spot into the fabric of space? And how could gravitational waves from inflation leave no trace in the CMB's polarization? These aren't just technical hiccups, they're cosmic curveballs, forcing us to reconsider everything from the nature of dark energy to the very geometry of spacetime. Perhaps the most humbling lesson here is how often our certainty crumbles under closer scrutiny. For decades, we've built towering theories, inflation, dark matter, the standard model, only for the CMB to poke holes in their foundations. The Hubble tension alone exposes a crack in cosmology's edifice, where two flawless methods for measuring the universe's expansion refuse to agree. It's as if the cosmos is teasing us, dangling answers just out of reach while revealing deeper layers of complexity. And that's the beauty of it. Science isn't about declaring victory. It's about chasing the next mystery, embracing the discomfort of not knowing. The CMB doesn't exist to confirm our brilliance, it exists to challenge it. So where do we go from here? New telescopes like CMB S4 and Light Bird are already gearing up to probe these anomalies with unprecedented precision, while theorists are spinning out wilder, bolder ideas to explain them. Maybe the cold spot will turn out to be a bruise from a colliding universe. Maybe the missing B modes will reveal flaws in inflation itself. Or perhaps the greatest revelation is still hidden, waiting for a future generation to connect dots we haven't even seen yet. That's why this isn't an ending, it's an invitation. Every anomaly in the CMB is a beckoning path, a chance to push further into the unknown. Whether you're a scientist, a student, or just someone who gazes up at the night sky and wonders, these mysteries belong to all of us. Support the missions, follow the discoveries, stay curious, because the universe isn't done surprising us yet, and the next great breakthrough might be hiding in the static of an old TV, the echo of a bang we're only beginning to understand.